Hello guys, and welcome back to another part in my DIY analog synthesizer project videos. Now in this video I'm going to be covering the topic of power supplies. Now why do we need a power supply? Well, the power supply is probably one of the most important components within your project, whether or not that actually be a wired powered supply or one you're using from a battery. So it's pretty much the heartbeat of the system. It's like trying to drive a car without no engine. It's not going to take you anywhere. Right, okay, so what I'm going to be having a look at today is just a couple of power supplies that I've tried and tested within my project, and just to sort of give you a little heads up, not to tell you to go out and buy these particular ones, because there's lots of other options out there. There's also some DIY projects, but just as a warning and a disclaimer, I will not be held responsibility for anybody blowing up their house or burning down their neighbour's house, etc. So please be careful when you're messing with electricity, because it doesn't always give you a second chance. Luckily enough, we have solutions which are sort of brought down to a safe working voltage in the form of what we have here, which is the wall wart, or whatever you want to call it, the AC or DC transformer adapter. It looks like so. So, like I said, there is some DIY projects out there which you can sort of have a go at from scratch. But if you're dealing with 230 sort of UK or whatever, 110, whatever it is over the seas, be very careful. Mains power supply will try and kill you if you do things wrong and end up in the wrong place at the wrong time and the wrong voltage. Right. Okay, so what we have here is my first power supply, or should I say my first PCB and power supply, which I obtained from, this one came from Frequency Central. Now what it is, Frequency Central basically do the bare PCB. Normally a lot of people use these for Eurorack. So you can either have two options. It depends on which types of regulator you use. We can either have the plus 12, negative 12 regulator, or plus 15, negative 15 regulator. Now what we need to do before that is get yourself a adapter. If we have a look on there, if you look on the adapter, it says AC adapter. It doesn't say anything about DC. Why is that? So what we're basically doing is we're taking an AC voltage, which let's just call that 230 volts for argument's sake, and that's our windings of the transformer, and we're converting that to a DC voltage, which we could say, I don't know, let's just say 18 volts. Made a mistake. Okay, let me start that again. So basically we're taking the 230 alternating current, that's our sine wave, our frequency, which is roughly about 60 Hertz in the UK, and we're converting that to 18 volts, stepping that down through the transformer windings to a safer working voltage, shall I say, which is 18 volts, about 18 volts AC, and we're still, as we can see, that's not an ideal waveform, or should I say an ideal power supply for what we need. We need to convert that to DC, which we will do through a make-up topology of components put together like so. So what we have here, you see these capacitors here, basically what they will do is help to suppress the ripple and basically turn out AC, half-wave rectifier, and then hopefully we will get a straight line of DC, which is ideal of what we need. So on our power supply here we have a rectification stage. So what we're going to have is a configuration of 4 power rectifying diodes. I may not have drawn this the correct way round. So we have our 4 power rectifying diodes all kind of linked in a ring here. And from here we're able to tap a couple of voltages out. So from our transformer windings, we're coming in, we're stepping down from say 230 to, I don't know, let's just say 18 volts. Remember, this is the alternating current side, we're rectifying that, and then we're hopefully getting DC out from both sides of this, so we could have say plus 18 volts DC, and we will also get minus 18 volts DC, and then we will have a series of capacitors. So if I get this the right way round, so from our negative side our polarity will be opposite, so don't forget to observe the polarity. So that's our capacitors here, which will help smooth out the ripple. And then our center tap here will give us our 0 volts, also known as our ground, which we see represented on the schematics either by the following symbol or sometimes just a pointing down arrow symbol, which is our ground. So if we look on the schematic and we see the ground symbol, that's basically the center tap of where the two voltages meet. Right. So what I did was I had a sort of search on eBay and looked for a mains power supply, an AC adapter, and what I found was a 15 volts 1.5 amp. I think you could probably go to about 2 amps as well, but 1.5 amp is enough to power my project. So when I actually measured the actual voltage of the AC power supply, it actually came out at about 18 volts, so it's actually about 3 volts overhead on what is actually prescribed. So when you buy this PCB order this PCB from Frequency Central, you will not get any of these components on it. So these are components. It will give you the sort of kit, the bill of materials, and you will have to hunt down the components yourself and actually solder them yourself. So this is a DIY kit. If you're a little bit experienced in soldering, it's not too hard to do. I mean, even I did it. I don't solder I can't solder to save my life. I managed to get this one up and get this one running, and you can see here, very importantly, you need these 2 little things here which are heat sinks, because these voltage regulators, which are just behind here, plus regulator and the minus regulator, they become quite hot. So we've got a couple of LED power indicators, and what I shall do is plug this in. And there we have it. If we look on the meter there, if we're going from the green, which is our ground, and the red, which is our positive voltage, the black is the negative voltage. So if I swap that to the other side, as you can see, that's our negative voltage. So what I've got in my one is a plus 15, and the positive 15 and negative 15 voltage regulator has been supplied by about 18 volts AC. So it's going through the rectification stage through the capacitors, filtering capacitors as large as possible, and we're getting that bipolar power supply which we would need for most dual rail op amps. I mean, there are some op amps which can run on sort of a single supply to ground, like say the LM3358, the LM324 quad op amp. So most of my projects, sort of the ICs that I use, say for instance, you know, we do require the bipolar power. So that is our first power supply. That is the Frequency Central power supply. I will leave a link in the description. Please go check that one out. It may not be suitable for your needs. It possibly could be suitable for your needs. And remember, you can supply this with, you can use 12 volt regulators. You just have to change to 15 if you want 15 plus and minus 15. Let's have a look at the second power supply solution, which is this one here, which I bought from eBay. Now if you have a look, I'll give you a bit of a close-up as we can see the board. Now this power supply came as a bare PCB again, and it also came with the components for around about 11 to 12 pounds, about the same price as the Frequency Central one. But as I said, the Frequency Central one doesn't give you the components. Now this one comes with all the components. The difference with this one, although it gives you bipolar supply, this one has variable regulators as opposed to the fix. So if I just show you this little resource chart that I've made, as we can see. So for your fixed regulators, you have your 7, 8, 12 for your 12 volts, your 7, 8, 15. This number this first letter stroke number could vary, but it's a 7, 8, 12 plus 12, 7, 8, 15. And if you notice on the negative, we'll have 7, 9. So you could be for 5 volts, you just take, you'll be 7, 8, 0, 5. Negative would be 7, 9, 0, 5 for minus 5 volts. So for the minus 15. And they come in this package, which is called the TO220. It's a sort of rectangular package, and you have a small sort of square plate with a hole in so you can fix to a heatsink for most voltage regulators. This is all through-hole components, by the way. SND solutions were probably very different. And this is the variable equivalents, which you have the positive, which is the LM317, and the LM337, which is the negative variable voltage regulator, and they're both linear. So again, I'm using exactly the same power supply. The funny thing was, before I bought this, I did ask the question from the guy, the seller, and sort of explained to him what my use was, what my idea of use was anyway, and he sort of said to me, well actually that's not going to work for you. So I was a bit okay. So as I looked at it, I kind of thought to myself, well, it has two sort of places to supply AC. How do I get the second one in? Because I only have obviously two from my AC adapter. So I run this, built this up, soldered it all together, found out it was working with my AC adapter from this side. So I measured the voltage out from this side, and I was getting the voltages I needed. So it just goes to show, don't always go by what people tell you. Right. And that includes me. So what we have here are variable regulators, and we can go from anything from about 2.5 volts, I think, up to about 32 volts. But your power supply, and this goes for the fixed regulators, your power supply voltage needs to be bigger than your output, your desired output, by say about, well, let's say as a rule of thumb, your desired output was say plus minus 15 volts. You'd need at least excuse my bad writing, you'd need at least sort of 18 volts AC in for these plus or minus 15 volts DC direct current. If, say, for instance, you needed 12 plus and minus 12 volts, which is quite a standard figure, you would need at least sort of plus 15 volts AC in. Or should I say 15? There's no plus on it because it's not bipolar, because it's alternating between plus and minus frequency. So why did I go for this solution? Well, this is the solution that I'm actually using at the moment. I prefer this one, and the only reason why I say that is because I can sort of tailor this quite precisely. So as we see here, if we look on the board, we have a couple of trimmers which are 10k sort of Bourne's type trimmers, and we can vary the voltage. So if we look here, we have the LM, and it actually shows the LM317 positive regulator, and the LM337, which is the negative regulator, variable regulator, and this is what you use to vary your voltage. So as we can see here, I'm in on the positive voltage, so I've trimmed mine to 13 volts plus 13, and I've trimmed my negative down to minus 13, so you can kind of get the symmetry between your positive and negative voltages a lot more accurate. Some of your voltage actual regulators, you will find your positive voltage will be slightly lower than your negative voltage. I'm not sure if that's got to do with how many components or modules actually draw more from the positive supply as opposed to the negative supply, apart from op amps, which are quite equal. So what I have in here is my screwdriver, and if you keep your eye on the meter, I'm going to trim the positive regulator. Sorry, that's the negative regulator. Let's go back to the positive, which was 13 volts. As you can see, that's gone up now. As you can see, as I change that, I can get that down to keep going. I think as a rule of thumb, kind of keep it roughly around the actual voltage, your input voltage, otherwise your regulators will get very hot, although they are sort of helped by a couple of quite big heat sinks, so you'll need a bit of thermal paste to couple that, as you do on, like I say, a computer CPU. Put a bit of thermal paste for the heat transfer. As you can see, these will get very hot. So as we can see there, I can vary that voltage all the way down. That's plus 10 volts. Let's take that back up to 13 volts, of which I normally have it. Just trim it. There, I'll leave it at that. And let's go over to the negative side. Which I have, as you can see, minus 13. Again, that's the LM337 variable voltage regulator, negative power out. And I will trim that. I can take that down, or take it up, even up to about plus 18. That's about my limit. I'm not going to try and go any further than that because I have never done it before so far. So my AC supply, if I show you in a minute, what I would do, as we can see, you can take that down to minus 8 volts, even, like I said, I think it goes down to about minus 2.5. So let's take that back up to plus 13. So I say, if you want that sort of symmetry and precision, I found this to be a better solution. Whether or not it actually gives you a cleaner power supply, a less of a ripple free and cleaner power supply, is another story. I don't have a proper sort of lab scope to measure that. And there we go. So if I remove from here, and then I'll go over to the AC voltage. And this is our incoming supply from the actual transformer. As you can see, I have 18 volts. Look on that meter there. That's 18 volts AC coming in, although the actual wall adapter says 15 volts AC. Anyway, that's all there is for now. I will leave a couple of links in the description, so please check that out for the power supplies, if I can still find this one, because it was a while ago I bought that particular power supply. I'll leave a link in the description, and also a few resources, schematics or DIY solutions. And as I said, please remember, high AC voltage will kill you, so please be very careful. If you don't know what you're doing, please go and get yourself a sort of a safer solution, as I did, and hopefully everything should be all good. Right, well, thank you for watching, people. Catch up very soon with some more tutorials and demos, etc. Right, thanks for watching, people. Don't forget to hit the like button, subscribe and share these videos.